We're going to begin the study of trigonometry today, and the word trigonometry literally means the measurement of triangles. Grade 10 specifically deals with right angle triangles, and if we take a look at my example here, I know it's a right angle triangle because this little box indicates that we have a 90-degree angle. In order to set up our primary trigonometric ratios, we need to understand how the different sides and angles are named. We always use capital letters for angles, and we use lowercase letters for the side lengths. We know already that the hypotenuse is the longest side of the triangle, and it's the side opposite from the right angle. So if you imagine a bow and arrow, if we pull back the bow and then shoot through, the side that we shoot through is going to be the hypotenuse from that 90-degree angle. There's two ways that we can name this. So clearly we can see that that is side HA. So capital letters if we're going to use two of them, but the more common way of labeling this is side T. So this here is angle T. The side across from it is a lowercase t. So again, we've got capital letter for the angle, lowercase letter for the side. Angle H right here, if we look at the side opposite, so again, imagine your bow and arrow, you pull back and you shoot through, the side that you shoot through is the opposite. If this angle is capital H, then my side opposite is lowercase h. So again, you can label it using these two letters here. We have two choices. So we can say it is side AT, or more commonly how we're going to refer to it is side H. All right, so in this triangle, we've already identified the hypotenuse. We've already identified the side opposite from angle H. The side that has not been labeled is this one here. It is side HT, or again, if you think about our arrow, it is going to be side A. So side A is opposite from angle A. So we can fill in here, this is either side HT or side A. We're going to take a look at a chart here. So I've got three triangles and we're going to fill in the chart just to make sure we're really clear on how to label these. My first triangle is triangle ABC. So that's this first example I'm going to take a look at. Again, we know the hypotenuse is always opposite from the right angle. So this happens to be angle B. So I know the side opposite from it is lowercase b. So I can fill that one in here. Angle A, we're looking for the side opposite angle A. So here is angle A. Imagine we pull back the bow and arrow. The side that you shoot through is the side opposite. So that is lowercase a. And the third side is with the side that we call adjacent to. Now the word adjacent means beside. I'm going to use a highlighter here. So in our triangle, the reference angle that we're looking at is angle A. We know already the hypotenuse is the longest side of the triangle. From angle A, the second arm that makes up that angle is this one here. The side adjacent to angle A cannot be the hypotenuse. So because this is the hypotenuse, this is the other arm adjacent to or beside angle A. So the side that is adjacent to it is angle C. And then likewise, if we take a look at using angle C as the reference angle, that means we start at angle C. The side opposite, if we shoot through this, is lowercase c. And adjacent to, again, remember, so if this is my reference angle, these are the two arms that make up that angle. It cannot be the hypotenuse, which we know is B. Therefore, the side adjacent to angle C has to be angle A. So I filled that in here. All right, if you think you've got this, I'm going to get you to pause the video. I want you to complete the remaining two examples here, fill in the chart, and then you can come back and see if you are correct. If you're not quite sure, I'll go through and do one more here. Taking a look at our second example, so we've got triangle DEF, that's our second one. The orientation is a little bit different, but again, we know that the hypotenuse is always the side opposite from the right angle. So here's my right angle. I go straight across, and this is side D. And you know what? Let's actually label these first. So if this is angle F, I shoot through here. I know this is going to be side F. And lastly, here is angle E. If we shoot through the side opposite, we know that's the side E, and then we can go from there. Okay, so the longest side in that second triangle is the hypotenuse D. If we use angle E as the reference angle, so if this is angle E, the side opposite angle E is lowercase e. The side adjacent to angle E, and again, remember, so these are the two arms that make up angle E. It cannot be the hypotenuse, so it cannot be D, which means the side adjacent to angle E is side F. All right, and then likewise, if we use angle F as our reference angle, so we start at angle F, the side opposite angle F is lowercase f. The side adjacent to angle F, these are the two arms that make up angle F. It cannot be the hypotenuse, so it's not going to be that one. So the side adjacent to angle F is our remaining side, angle E. Okay. And then finally, similar with this one, I'm going to start with labeling the sides. So this is side I, opposite from angle I. Side G is opposite from angle G. Side H is opposite from angle H. And again, I'm using lowercase letters. In that triangle, my hypotenuse, the longest side is side I. If we use G as our reference angle, the side opposite G is lowercase g. The side adjacent to G is H, because here's the two arms. It cannot be the hypotenuse, which means it has to be that one. So I'm just going to fill this in here. So this is going to be G and H. And finally, if I'm using angle H as my reference angle, the side opposite from angle H is side H. I'm going to fill that in at the bottom. I'll scroll this up in a second. And finally, these are the two arms that make up angle H. It cannot be the hypotenuse, so the remaining side, G, is the side that is adjacent to angle H. So I can fill that in here. All right, there's a pattern to this. So number one, did you get the chart filled in correctly? And then what do we notice? So in each of these cases, you might see that these two sides are interchangeable, depending on the angle that we happen to use as the reference angle. In all three of these examples and in all right angle triangles, the hypotenuse will never be the opposite nor the adjacent side. So that's the first thing we're going to fill in here is the hypotenuse will never be the opposite or the adjacent. And the second thing is you're going to notice that the side opposite angle A is A, the side opposite angle C is C. So the reference angle we're using indicates which side is opposite, which side is adjacent. If I'm using angle E as my reference angle, the opposite is side E, but if I'm using in that same triangle angle F as the reference angle, that side F is now my opposite side. All right, so we've summarized some key points that we need down below the chart. There are three primary trigonometric ratios. We're going to begin today with the tangent ratio. I have four triangles in my diagram here, and I'm going to tell you that they are all right angle triangles. So I'm going to draw in my little box here to indicate that those are 90-degree angles. And we're taking a look at the ratio between different sides in the triangle. So if I start down here, side BC is the height of my smallest triangle, and it has a length of 3 meters. Side AC is the base of that triangle, the smallest one, and it has a length of 4 meters. So I'm going to fill in here, BC is 3 meters, AC is 4 meters. The units are the same, so I'm just going to leave them off. They would divide out. My second triangle, this one here, is triangle DEA. DE has a length of 6 meters. AE has a length of 4 meters. So I'm going to fill in here this ratio is DE is 6 meters, AE is 4 meters. My third triangle here is the next one I'm looking at. FG is the height of that triangle at 9 meters. And AG is the base of that triangle. And I've kind of gone down here a little bit. So that's going to be from here to here is 12 meters. So we can fill that in. And then my largest triangle, HI has a height of 12 meters, and again, if I go down here, this is the base of that large triangle at 16 meters. So my ratio is 12 to 16. Now, what do you notice about those ratios? You should notice they are all equivalent. When I have them filled in properly, they all reduce down to 3/4. All right, so we've gone down here and filled this in here. So each of these triangles is a similar triangle. If they all contain a 90-degree angle, and the other angle that they all contain is angle A, so that's the angle that's kind of embedded into each one of these triangles. We know a triangle has 180 degrees in it, so if they all have the same right angle, and if they all have the same angle A, we know this angle is going to be the same in all 4 of those cases. So all of my angles are equal, and all of my sides are proportionate. Going back to my ratios that we started with here, remember that if we take a look from angle A, BC happens to be the side opposite. So if this is my reference angle, this is my side opposite in my smallest triangle. AC happens to be the side adjacent to angle A. In my second triangle, DE, so again from angle A, if I use that as my reference angle, DE happens to be the opposite side. AE happens to be the adjacent side. Similar with these two. If I use angle A as my reference angle, in each of those cases, this is the side opposite, and this is the side adjacent. No matter how big or how small my triangle is, if this angle is the same, we know that the ratio of the side opposite to the side adjacent will always be equivalent. In relation to angle A, if I use that as my reference angle, each of these 4 ratios here compares the opposite to the adjacent. So we are comparing the opposite to the adjacent, and those ratios are dependent on that angle A. That's our tangent ratio. So we know if we have similar triangles, every time we have a reference angle A, the side opposite that angle divided by the side adjacent to that angle is always going to give us the same ratio. All right, so we're going to take a look at how to do this on the calculator. Anytime we're dealing with the 3 primary trigonometric ratios, we want to be in degree mode. So what you're going to do is you're going to go into the mode button here beside second function, and then right here is degrees. So you can see the default is radians, and it's because when we get to grade 12 and beyond, we tend to work in radian mode. It's a little more intuitive for higher level mathematics. But for our purposes, we're going to go to degree mode. So we're going to go down and we're going to arrow over. So the cursor is flashing on degrees. We're going to press enter, and then you can move over and see that we are now in degrees. To get out of here, we're going to go second function, mode, because you can see that puts us into quit, so we quit out of there. All right, that's the first thing, and that's really important. You're going to get different answers. You're going to get the wrong answers if we're not in there. So we always need to make sure that we put the calculator into degree mode first of all. All right, so when we go to determine the ratio, if I have a triangle that has an angle of 0, this is my tangent button, so I'm going to go tangent of 0, and that gives me 0. And that makes sense, because if I have a triangle, let's say this is my triangle, if this is my angle, where angle A was, my opposite side is 0. My adjacent side, doesn't matter how long this is, if I have an angle of 0, my opposite is 0. I basically have the 2 arms of the angle are right on top of each other. Compare that with, if we take the tangent of 15, so I'm going to go in here, we're going to go tangent of 15, my ratio of those 2 sides, opposite to adjacent, is going to be that. Now it wants us to round to 4 decimal places. So this is my 4th decimal place. Look at the number that comes after. Because it's not 5 or higher, then we're just going to leave it as is. So this is going to be 0.2679. 2679. And again, this makes sense. If this is my triangle, and this is a rough estimate, let's say that's my 15-degree angle. So now I know if I were to measure this side opposite, divide it by this side adjacent, that is the measurement I'm going to come out with. Now we're going to double that angle. We were at 15, we're going to double to 30. So I'm going to go in here and I'm going to say the tangent of 30 is equal to that. Okay, and again, we're going to round to 4 decimal places. This is my 4th decimal place, the 3, because the 5 comes after, that's going to bump that up. So our ratio comparing the opposite to the adjacent is 0.577, and that's going to become a 4. Okay, so my triangle, my angle's growing, and I mean, this is not measured, this is a rough sketch, but now, if this is 30 degrees, so this is angle A, it's now 30. So my opposite side divided by my adjacent side is going to have a larger ratio. All right, we're going to continue on here. So now I'm going to do the tangent of 45 degrees, and my ratio is 1. Okay, because we want 4 decimal places, I'm going to go 1.0000. Okay, so 45 degrees. We know that's half of 90 degrees. So my right angle is right here. This is now 45 degrees. Okay, so think about what we know about triangles. We know a triangle adds up to 180 degrees. So if this is 90, these two angles have to also add up to 90, which means this is also 45. So this, again, makes sense. If this is my angle, my opposite compared to my adjacent, this side is going to be the same as this side. All right, tangent of 60 degrees. So we're going to put this in here. And to 4 decimal places, 1.732. 1.732, and we're going to bump that up to a 1 because the next number is a 5. Okay, so again, these are getting a little bit larger. So now this is 60 degrees. There's my right angle. This is now 60 degrees. The opposite side compared to the adjacent side, in order to get those two sides to connect, this opposite side has to be larger than this adjacent side. And this is not drawn to scale, but if you were to take a look, you'll see that's what's happening. Okay, so we're going to keep going here. So the tangent of 75 is now 3.7321. So 3.7321. The tangent of 89 is 57.2. Okay, now this is a 6, which bumps this to a 10, which bumps this to a 10, which bumps this to a 9. So we're going to have 0.2900. Okay, so this is interesting. I tried to draw this on the side. So in each of these cases, I've been putting my right angle on the left side. So if we continue, this is my right angle triangle. 89 degrees is almost a right angle. These two have to add up to 90 to get our 180 degrees in a triangle, so I know this is 1 degree. So in order to draw this triangle, and it isn't quite drawn to scale, but you can see, hopefully, that if this is 89 and this is 1, we're going to have something like this. So from my reference angle of 89, this opposite side is quite a bit longer than the adjacent side, giving us that large value when we compare the two. And then when we go to do tangent of 90, so this is going to be our final one here. So if I put in, I'm going to clear this out, tangent of 90, we end up with an error. So it says that there's a domain error, and we can go to the error if we want. And why is there an error? Well, again, think about this. If this is my right angle triangle, so there's my 90 degrees. If I put a second 90 degree angle there, I'm just going to fill that in there too. I can't connect the triangle. That's impossible. So this one, our calculator says error. We can't do that. All right. So in each of these cases, what we're doing is we're saying, okay, given an angle in a triangle, we know tangent compares the opposite side to the adjacent side. We can get the ratio of those sides, similar to what we did up here when we were developing this. If I take, in this case, it was angle A, and divide those two sides, in each of those cases, I was getting 0.75. Given an angle in a right angle triangle, we can figure out the ratio of those two sides. We can also work backwards. If we know the ratio of the opposite compared to the adjacent side, because it's the same in every triangle with that angle, we can also figure out what that angle is. So we're going to take a look at how to do that. I'm going to pull up my calculator here once again, and in this case, I'm going to take the first one. We're going to take the inverse. So you can see above tangent here, I have tangent to the power of -1. That's the inverse. So I'm going to go second function tangent, and then there's that little -1, and I'm going to enter a ratio of 1. When I do that, I get 45 degrees. Now we know that's true because up here, if we go back to what we just did, I know if I have a tangent of 45, if my triangle contains a 45-degree angle, the opposite compared to the adjacent, that's an isosceles triangle. They're going to be the same, so that's 1. So if my ratio is 1, we know that angle is 45 degrees. So A is 45 degrees. Similar to that, we can also take a look at the second one. So if the ratio of the opposite divided by the adjacent is this, I can use that to get the angle. So I'm going to go second function tangent to take the inverse. We're going to go 0.466. And we know any triangle, when we divide the opposite to the adjacent and get that ratio, that tells us, and again, we're rounding to the nearest degree, so because this is a 9, that's going to bump that to a 5. So I know that angle B has to be 25 degrees. All right, so this happens to be a decimal. They've already divided the opposite by the adjacent for us. Here it's left in fraction form, so you have a choice. We know that this is 3 over 5 is 0.6, so you could enter 0.6, but if you ever have a fraction, we're going to go second function tangent. We could always just put it in by going 3 divided by 5, close the brackets, and then that will give us the ratio. So to the nearest degree, that's going to round to 31 degrees. All right, you try the last two, and you can pause me for a second, see what you get, and then I will fill these in as well. Okay, so to the nearest degree, I know angle D is going to be 52 degrees. And the last one you can do is going to be 49 degrees. All right, and again, if you go back up here and compare them. So a ratio of 1.28 is going to be in between 1.0 and 1.73. So we know the angle needs to be between 45 and 60, in which case it is. All right. This is the last thing for today. So we're going to start to actually apply this. We spend a lot of time developing where this is coming from. I don't want you just punching buttons on the calculator and seeing numbers spit out. We want to have some idea as to what those numbers represent. Here's how we do this. So in each of these 3 examples, our goal is to find the value of the missing side. So we're going to say, okay, what's our reference angle? Obviously, we can calculate this angle. We know these 3 have to add up to 180, but as much as possible, go with the information you're given. So my reference angle is 40. From 40, I know that this is the opposite side. I know this is the adjacent side. This is my hypotenuse because it's the longest side opposite from the right angle. We can set up a ratio. So the tangent of 40 degrees equals the opposite side divided by the adjacent side. And then this creates a proportion. So we actually have a denominator of 1 here. And so in any proportion, we can solve it by cross multiplying. So I'm actually going to just multiply that in my calculator. So we're going to go in here. We're going to say, okay, tangent. Now notice there's a bracket that pops up. I'm going to put 40. You have to close the bracket. We're going to multiply that by 5. We're going to press enter. And when we do that, we've got x is equal to 4.2 centimeters. If it doesn't specify, we usually round side lengths to the nearest tenth and then angles to the nearest degree. All right, my second one. My reference angle is 62. This is the side opposite from that. So we can even just write those on here. So this is the opposite. This is the adjacent. So set up your ratio. We know the tangent of that angle. We can figure out the opposite divided by the adjacent. And again, the denominator is 1. If we're looking for x, we can cross multiply. 1 times 21 is just 21. So we're going to go 21, and we are dividing that by the tangent of 62. And again, because we're looking for a side length, we're going to round to the nearest tenth, and x comes out to be, once we round it, 11.2, and then just take a look at your units. In this case, it's going to be meters. And then in my final example, we're now looking for the angle. It's still really important we set up the ratio the same way. So it's going to be the tangent of that angle equals, and actually let's go back and write this in here. So from this angle, this is my opposite. So I'm going to put in here, this is the opposite. This is the adjacent. So opposite, this is in inches now, divided by adjacent. And so again, remember, when you put this in your calculator, oh, sorry. I'm going to move this over here. So when we put this in our calculator, we're going to now, because we're looking for an angle, we're going to go second function tangent. We're going to go 15 divided by 18. And when we do that, angles we tend to round to the nearest degree, unless it says otherwise. X is 40 degrees.